This video will be covering section 5.7, Properties of Matrices. We have three objectives. We will start by performing basic matrix operations, which will include matrix addition, matrix subtraction, scalar multiplication, and finally matrix multiplication. We will then apply algebraic properties to those matrix operations, and then the final one we will apply matrix multiplication to solve application problems. Okay, so some review of some basic terminology. So here we have a general matrix. The dimension of this matrix would be m by n. The m, remember, the first component here is the rows, and the n is the number of columns. So we've got m different rows and n different columns. When we want to refer to a single element of the matrix, it has two subscripts. So this first element that you see here is A sub 1, 1, which refers to first row, first column. If we look at the element A23, this is A sub 2, 3 is the element in the second row, third column. So the first component is always the row that it's in, second component is the column that it's in. A general element of a matrix would be referred to as A sub ij, meaning it is in the ith row and in the jth column. Some special types of matrices that we have. First one is a square matrix. A square matrix is simply when the number of rows is equal to the number of columns. So you could have any size of a square matrix. This is a 2 by 2 square matrix, but they can be as large as you need. Then a row matrix is simply a matrix that has only one row, but it could have as many columns as you need. So this would be a 1 by 3 matrix, one row but 3 columns. And then a column matrix, same idea, but has a single column but could have multiple rows. So this would be a 2 by 1, 2 rows but only one column. When we have two matrices, we say that they are equal if and only if they have the exact same dimension, but they also have to have the exact same corresponding elements. So if you look at these two matrices, they are both 2 by 2s, so they have the same dimension. However, the corresponding elements are not the same. Notice all four numbers are matching the four numbers here, so in terms of a set, they would be the same set of numbers, but they're not the same matrix because you need to have the exact same number in the exact same position. So this would have to be a 2, and this would have to be a 1. They have to be exactly the same. That's the only way we get equal matrices. Okay, let's try applying that property. So here we have an equation with two matrices. They do have the same dimension, so that means it is possible for them to be equal. So now we just need each component to be equal. So we could say the first component, 2, has to be x. The second component in the first row has to be y. P would have to be equal to -1, and Q would have to be equal to 0. And that's all there is to that. That solves for all four variables there. X is 2, y is 1, P is -1, and Q is 0. Just setting each component equal to each other. All right, the next one, we have a problem here because this first one is a 2 by 1, and then this one is a 3 by 1. They don't have the same dimensions, so there is no way for these to be equal. This one is just not possible. In order to be equal matrices, they have to start off with the same dimension. Okay, our first operation that we want to perform on matrices is addition. In order to add two matrices, that can only be done if they have the exact same dimension. So if they don't have the same dimension, you just can't add them. Once, if they do have the same dimension, then the way you add them is exactly what you would expect. You simply add the corresponding components together. So first thing to notice, these are both 2 by 2s, so we can actually add them together. So when we add them, we would get 5 plus a -4 in the first row, first column, -6 plus 6 in the first row, second column, then 8 plus 8, then 9 plus a -3. All right, then just simply add those components together. So we end up with 1, 0, 16, 6. And that's it. That's all you have to do. You're just adding those corresponding components together. All right, the next one, again, dimensions are the same, 3 by 1 and then 3 by 1. So we can add them, and we just add straight across here. So we're going to get -4, 8, 20. So one thing to notice, when we add two matrices, the resulting matrix has the same dimension as the original matrices, which is what you'd expect, but we'll see when we get to matrix multiplication that's not true in that for that operation. All right, next one says do a plus b if a is equal to this and b equals this. Well, here we have a problem. This is a 2 by 2 matrix, and this is a 2 by 3 matrix. They don't have the same dimension, so we can't add them. This one is just not possible. In order to add them, you have to have the same dimension. So you can't just simply add this matrix onto the front of this matrix. We just have not defined what this even means. Just not possible. Okay, a couple more special matrices. The next one is a zero matrix. A zero matrix is any matrix, no matter what its dimension, that's filled with completely zeros. So this would be a 1 by 3 zero matrix. It's a row matrix. That's a zero matrix. Here is a 2 by 3 zero matrix. You could have it being a square matrix, any dimension you want. Zero matrix simply means all the elements are zero. Okay, so if we have a zero matrix, it should be pretty obvious that the zero matrix behaves like the normal zero, meaning that if you take a matrix and you add the correct zero matrix to it, you just get that matrix back. So provided these two things have the same dimension, that A and the zero matrix have the same dimension, you should just get A back. This then enables us to define an additive inverse. So just as in algebra, an additive inverse is any element that satisfies this equation. If you take A and you add B to it and you get 0, then those two things have to be additive inverses. So this, the way we find this is we just define this matrix B to be -A, as you see here. And the way you get that is you simply take the negative of all the elements inside, which is exactly what you'd expect. So the additive inverse of a matrix A, you just put negatives inside of the matrix on each element. This then enables us to define matrix subtraction. So just as with numbers, we actually define the difference between numbers. If you take A minus B, it's really A plus the opposite or the additive opposite of B. So we can do that with this, and all this really amounts to is we're just going to distribute the negative through here, or think of it as we're going to subtract each of the elements, each of the corresponding elements in that matrix. So let's do that. This would be -5 minus a -3, 6 minus 2, 2 minus 5, and 4 minus a -8. All right, so that should give us -2 in the first component, then 4, -3, and then 12, it looks like. So that's all you do. You're just subtracting the corresponding elements. Again, the only way this can be done is if the dimensions of your two matrices are the same, which they are. Both of these are 2 by 2. All right, next one's going to work the same way. We're going to get a 1 by 3, so it will be 5, 1, then be careful with your signs. So this negative will cancel that out, so you're going to get a +4 in that final component. All right, so far pretty simple. Addition, subtraction of matrices, pretty easy. One more of these. We're going to try to do A minus B, but always pay attention to the dimensions. These are not the same dimension, so you can't subtract them. This does have an additive inverse, but we can't add these together because the dimensions aren't the same. So again, not possible. Okay, next operation is called scalar multiplication. So when we refer to a scalar is just a number. There is a difference between numbers and matrices, right? Matrices are an array of numbers arranged in some kind of a rectangle, which has a specific order to it. So this is not just a single number, it's a collection of numbers in a sense, but a scalar is just a single number. So that's all that fancy word means. You can think of it like it's changing the size of the matrix. It's scaling it up or scaling it down. So the way we do scalar multiplication is exactly as you'd expect. If I'm going to do 5 times that matrix, I just multiply every element inside the matrix by 5. So it's 10, negative 15, 0, and 20. We've scaled it up. Every element gets multiplied by that number. You can do it with any type of number, so fractions will work as well. So if we take 3/4 times 20, the 4 will cancel with the factor of 4 and the 20, so you'll get a 5 here. 5 times 3 is 15. 3/4 times 36, again, divide 36 by 4, you get 9, times the 3 is 27. 3/4 times 12, divide the 12 by 4, you get 3, multiplied by 3 is 9. And then 3/4 times negative 16, divide negative 16 by 4, you get negative 4, times the 3 is negative 12. Now, with scalar multiplication, it doesn't matter what the dimension of the matrix is. You can always perform scalar multiplication no matter what. All right, the next table here just indicates that scalar multiplication behaves nice. We have couple different distributive properties here. This is saying that if you have two scalars added together that you're then going to multiply by a matrix, you could actually distribute the matrix through, do each individual scalar multiplication, and then add those together. Or if you have a matrix sum here and a scalar on the outside of it, you could distribute the scalar in first. So pretty much what we would expect. We also have some associative properties. This says if you're going to do scalar multiplication followed by another scalar multiplication, you could just multiply the two scalars together first and then do the multiplication on the matrix. And then this is just another version of that associative properties. This basically just tells us scalar multiplication behaves nicely and it behaves the way we would expect. Okay, so we've done matrix addition, we've done matrix subtraction, and scalar multiplication. So now we want to do matrix multiplication. This one, unfortunately, is quite a bit messier than the other ones. So before we write out the general rule, let's just look at an example that's already worked out here for us. So the idea for this is we're multiplying these two matrices. You'll notice they don't have the same dimension, but there is an important relationship with their dimension. This one is a 2 by 3, 2 rows and 3 columns, and this one is a 3 by 2. In order to multiply A times B, the number of columns in the first matrix has to equal the number of rows in the second. And you'll see how that works actually down here. Okay, so what we do to get the elements in the product is you take the first row of the first matrix and you multiply it by the first column. You take the corresponding elements of the first row, multiply it by the corresponding elements of the first column in the second matrix. So we have negative 3 times negative 6, that's right here. Then 4 times 2, right here. Then 2 times 3, right here. All of those products get added together. So you'd have 18 plus 8 plus 6, which should give you this 32 here. So that entire, we call this a linear combination here, adds up to this number here. That gives us our element in the product. And then you keep that process going. It's always rows by columns, and then row by column. So let's look at this set of numbers here. We did negative 3 times 4 right there, 4 times 3 right there, and 2 times negative 2 right here. Multiply those and add them together, and you get negative 4 in that position there. Now, to get the second row here, we have to use the second column of the first matrix. So again, though, it's row multiplied by column. So 5 times negative 6, 0 times 2, 4 times 3, and then all of that added up gives us the negative 18. And then that final element is given by the second row by the second column. So 5 times 4, 0 times 3, 4 times negative 2. And add that together, that gives you 12. So let's look at the dimensions again. Remember, we said this was a 2 by 3, and this is a 3 by 2. Whenever you're doing matrix multiplication, these two things have to match, and the resulting matrix you can see is a 2 by 2. It doesn't match the size of either one of the first two matrices. The resulting dimension will always be the number of rows of the first matrix by the number of columns in the second. So this is the resulting dimension of your product. So a lot more going on here. Let's look at this in general. Okay, so I have two general matrices here. So this is an M by N matrix, and this one is an N by P matrix. Let's actually record that here. It has M rows and N columns, where this one has N rows and P columns. So we can multiply these because number of columns in the first matches the number of rows in the second. We also know that the final matrix will have dimension of M by P. It will have M rows and P columns. You can see that with the subscripts here. Remember, the first subscript is the rows, so we can see M different rows. Second subscript is the number of columns, and there are P columns. Okay, so how do we get the elements in that? Well, we do the same procedure that we did before. So for example, this first element here was found by taking the first row and multiplying it by the first column. So A sub 1, 1 times B sub 1, 1, A sub 1, 2 times B sub 2, 1, and etc. all the way down. That's how you get the first element. The second element would have been found by taking the first row again and multiplying it by the second column. So this multiplied by this. Notice that the elements here, they okay, so what about a general element? So a general element, remember, would be something like this guy. This is the element in the ith row and the jth column. So to get this, we would need the ith row of matrix A, and it would be multiplied by the jth column of matrix B. And again, it would be this element times this one. A sub I1 times B sub 1j. That's written right here. Then A sub I2 times B sub 2j, second element. And you just keep going until you get to the final element, which is A sub In times B sub nj. The thing to notice here is that the second subscript always matches the first subscript, and that's because this is in the column position corresponding to the row position for this element, and that's true all the way across. So this formula right here actually defines how to do matrix multiplication in general. Every single element in this matrix on the right is generated by this expression here. Okay, so let's try using some of these properties. Let's first just talk about when matrices can be multiplied or not. Suppose I give you a 3 by 2 matrix and I give you a 2 by 4 matrix. The question is, can you multiply them? Well, let me just write this out. We got an A times B, put the dimension below it here. That's a 3 by 2. This is a 2 by 4. Can we do that product? Yes, we can, because those match. As long as these match, then yes, we can multiply those. All right, if we multiply them, what is the dimension of the resulting matrix? Well, the resulting dimension is a 3 by 4 matrix. So the product AB, if you complete that matrix, you get 3 by 4 as its dimension. 3 rows, 4 columns. Okay, now, so we did AB. What about B times A, if we flip this around? Up to this point, we're completely, everything we do in math has been commutative, meaning that A times B is equal to B times A. But what about with matrices? Is that still true here? Well, if we flip this around, B times A, B is a 2 by 4, and A is a 3 by 2. These do not match. So no, it is not possible to multiply those two together. So that means in general, no, it's not commutative. A times B is not necessarily equal to B times A. It will be in some particular cases, but not in general. And this is one example where A times B is not the same as B times A. Okay, so let's try to actually do some multiplication here. So let's put in the dimensions before we get started. This is a 2 by 2 and this is a 2 by 4. So can we even do this product? A times B, we can. The resulting product that we're going to get is a 2 by 4 matrix. Okay, so I'm going to rewrite the matrices here. Okay, so to do this product, we're going to start with the rows of matrix A and multiply them by the columns of matrix B. You always want to just remember you do rows by columns. That will be how we always multiply matrices. So the first element is going to be 1 times 1, this one times that one, plus negative 3 times positive 3. So that's just the first element in the matrix. We're going to have 4 of these across. So then we go to the back to the first row and multiply this row by this column. So that's going to be 1 times 0, and then negative 3 times 1, plus negative 3 times 1. So this is second element in the first row. Then go again, first row by the third column. So we stick with this first row until we've done all the columns. Okay, so that's going to be 1 times negative 1 plus negative 3 times 4. And then now on to the final one. It'll be this row by this column here. So 2 times, let's flip that around, doesn't matter, but just to be consistent here, 1 times 2 plus negative 3 times negative 1. Alright, all of that was just for the first row. Now we got to go through and do the second row. So it's going to be this row multiplied by the first column. 7 times 1 plus 2 times 3. Then now to the second column. So 7 times 0 plus 2 times 1. Next column, 7 times negative 1 plus 2 times 4. Then 7 times 2 plus 2 times negative 1. Alright, and then we just need to simplify. So first one's going to be 1 minus 9. Next one is just going to be a negative 3. Then negative 1 minus 12. Then 2 plus 3. Second row, we've got 7 plus 6, 2, negative 7 plus 8, and 14 minus 2. And finally just simplify those to get negative 8, negative 3, negative 13, 5, 13, 2, 1, and 12. So you can see much more painstaking process than simply addition of matrices. But also notice, as we said at the beginning, we said our final matrix, the product should be a 2 by 4. You can see this is a 2 by 4 matrix. Alright, what about the other product? What if we want to do B times A? Well, the dimensions of B is 2 by 4. The dimensions of A is 2 by 2. And these do not match. So that means that product is not possible. It's undefined. There's no way to actually do that product. Okay, let's do one more of these. Let's do this with square matrices. Now, one of the nice things about square matrices is the product, if they have the same dimension, the product will always be defined. And in both directions it will be defined. So since this is a 2 by 2 and this is a 2 by 2, both A times B and B times A will be defined. And then not only that, the resulting matrix that you get is a 2 by 2 matrix, meaning the same size as what we started with. So you can always multiply them and the answer always gives you the same size as what you started with. Alright, so we'll rewrite the matrices. And so again, it's rows by columns. So I'm going to write a little bit less this time. So we're going to do 1 times -2, that's just -2. 3 times 0, that's a 0. Move on to the second element. So it'll be 1 times 7, that's 7, plus 3 times 2, which is 6. So that's our first row. Second row, -2 times -2 is 4, plus 5 times 0 is 0. Okay, let's get the last element in the matrix. So we need to take this row and multiply it by this column. So that's going to be -14 plus 10. 5 times the 2 gives us the 10. All right, now we can go ahead and finish it. So we have -2, 13, 4, and -4. So this is our product AB. Okay, so we can now do the other product. So again, the question is, well, this is the first one where we can do the reverse product. Will it come out as this same matrix? Well, let's find out. So again, I'll rewrite the matrices. Just make sure you are consistent and you actually do the order that they're specifying here. All right, so again, rows by columns. So the first element is going to be -2 times 1, -2, 7 times -2, minus 14 there. Then first row by the second column, so that is -6 plus 35. And then second row by first column to get this element will be 0 minus 4. And then last one is 0 plus 10. All right, combining those gives us -16, 29, -4, 10. So this was the product BA. And we can see this is not the same. That is not the same. I guess we don't need to do that. So this is not the same as the previous one here. Those two matrices, those two products don't come out the same. So we've established again that when it comes to matrix multiplication, A times B does not have to be equal to B times A. In general, it will not be. Matrix multiplication is not commutative. All right, so that's what this box is saying again here. But matrix multiplication does have some nice algebraic properties. So it is associative, meaning that if you had 3 matrices you were going to multiply, it doesn't really matter which product you do first. The order in which they're written matters, but the grouping does not. So in this case, we could do A times B and take that matrix and multiply it by C, or we could do the B times C but multiply by A after that with A on the left-hand side. So it is still associative. It is also distributive, so if you've got the sum of 2 matrices and then you're going to multiply by A, you can do the matrix multiplication on each one first, and it works in the other direction as well. So it has all the same properties with the exception that it is not commutative. Okay, last example is an application of matrices. So let's go ahead and read the problem. It says a contractor builds 3 kinds of houses, models A, B, and C, with a choice of 2 styles, colonial or ranch. Matrix P shows the number of each kind of house the contractor is planning to build for a new 100-home subdivision. So here's matrix P. It's saying they're building no colonial model A's, but they're going to do 30 model A's that are ranch style, 10 model B's that are colonial, etc., all the way through. So this is every type, every model with also its style. Okay, so it says the amounts for each main materials used depend on the style of the house. These amounts are shown in matrix Q. So matrix Q is here. So it's saying for a colonial style, they're going to be 10 units of concrete, 2 units of lumber, 0 of bricks, 2 shingles. So, and same thing for the ranch style. So it's just an array recording all of the different amounts of materials in each one. And then matrix R gives the cost in dollars for each kind of material. So concrete is 20 per unit, lumber is 180 per unit, etc. And I am assuming these are in dollars. And then here it just tells us what each unit of measure is. So concrete, these numbers here are in cubic yards. Lumber is in board feet. Bricks is in thousands of bricks. So this is saying we have 20,000 bricks for the ranch style. And shingles is in 100 square feet. So 200 square feet for the colonial and 200 square feet for the ranch, which seems quite a bit low, but we're just going to stick with their numbers. Okay, so these matrices are just organizing all the information in this problem. So let's look at what they want us to solve. So the first question is, what is the total cost of materials for all houses of each model? Now, we can definitely solve that type of problem without using a matrix, but we will see through this that the matrix gives us a nice organized way of doing this. So the first product that we would do is we would take P times Q. We know we can multiply these matrices because this is a 3 by 2 and this is a 2 by 4. So we can multiply them, and what we get, as you can see here, is a 3 by 4. Now, I've already labeled what the things are here, but you could know what the numbers correspond to by looking at what the rows and the columns referred to. So the rows on this first matrix, I'm just going to label it here, each of these rows are models. Right? If we go back to P, these were all the models in the rows. And then the columns on this matrix was material, which means this matrix down here is models, which you can see that right here, by materials. So for model A, it needs 1,500 units of concrete for all the model A houses, right? These are the number that we're building. So out of the 30 model A houses, we need 1,500 units of concrete. For the 30 model A houses, we have 30 units of lumber. We have 600 units of brick, all found by just multiplying these out. Okay, so that gives us the total amount, but we were supposed to do cost. So that's where we're going to take this new matrix that we have and multiply it by the cost matrix that you see over there. So again, I've already done that. So also notice, let's look at the dimensions again. This is a 3 by 4, and this is a 4 by 1, 4 rows, 1 column. So the resulting matrix out of this has to be a 3 by 1, which you can see we get here. So again, to identify what these numbers mean, think about the rows of this. The rows of this matrix were again models, and then the column of this is cost. So the resulting matrix is going to be models, which I've labeled on the right, by cost here. So model A, the total cost for building all the model A's, $72,900. The total cost for building all the model B's, $54,700. And model C, total cost for all of them being built, not each individual one, all of them, is $60,800. Okay, part B says how much of each of the 4 kinds of materials must be ordered. Well, we can go back and actually use the matrix PQ that we already found in the previous step to answer this. This matrix gave us all of the materials for each individual model. So to figure out the total amount of concrete that we need, all we would have to do is add this column. Add them all up, add all of that column to get all of the lumber, add this column to get total units of brick, and add that column to get total units of shingles. So we're going to refer to that new matrix as matrix T. The operation we did here does not really correspond to any operation we talked about today. This is just works. If you add this column down, it gives us the total of that column, total amount of concrete, etc. So this tells us how much of each must be ordered. Okay, so last part says, what is the total cost of the materials? So total cost of the materials we can find by taking the total amount of the materials, right? This is amount of each material, and multiplying it by cost. Notice this is a 3 by 1 by 4 matrix, 1 by 4, and this is a 4 by 1 matrix. So when we multiply those, we can multiply them because the number of columns is equal to the number of rows here, but the resulting matrix should be a 1 by 1 matrix. In other words, just a single number. So we take all of the concrete, that's what this represented, multiply it by how much each unit of concrete costs. Right? If we actually were to write this out, this would be 3,800 times 20, total amount of concrete times its unit cost, plus total amount of lumber multiplied by its unit cost, plus total amount of brick by its cost, plus total amount of shingles times its cost. Adding all of that up should give us this 188,400. So the main point of the problem was just showing you that something it's a basic algebra problem, but it can be organized very nicely, very succinctly using matrix multiplication. This is not the only type of application. We will see that matrix operations can be used to actually solve a linear system of equations. We'll cover that in the next section. All right, I believe this was the last example, so hopefully this makes sense. If you are having issues with any of these problems, make sure you email me, and we'll see you guys in the next video.